Hello friends, next we are going to continue the next setting out method of the curve, that is angular method. Before that, as a recap for the linear method, we have seen about the radial offset and the tangential perpendicular offset from the tangent. We see a small problem in that. The angle of intersection of a circular curve is 45 degree 30 minutes and its radius is 198.17 meter. Point of commencement is at station 0 plus 700. Compute the right angle offset from station 0 plus 736.58 on the curve to tangent through PC. Right. So what they have asked is compute the right angle offset. That means it is a perpendicular offset they have asked, not the radial offset. So they have asked about the only one offset distance. So this x has to be determined, and they have given some values, say station 0.700, that is point of contact, this chain age, and chain age at curve is A, at A is 0 plus 736.58, right? So this is the point they consider for it. The perpendicular offset has to be set out. This distance they are asking, and they have given, say, the radius of the curve is 198.17 meter. So from the origin to the point of commencement, it is 198.17. If you drop the line perpendicular to that radius, so this portion becomes x, the remaining portion is 198.17 minus x, and this obviously the radius of the curve. From this you are able to get the x. We have already derived the derivation. So let's see, length of the curve from point of commencement to A, length of from here to here, we need to determine the length of the curve. What the given thing, 0 plus that is 0 point plus 700 meter. From 0 means starting point plus 700 meter, and it continues from 0 to 736.58. so the length of the curve s is equal to 736.58 minus 700, which gives 36.58 meter, right? So the angle subtended by the arc s, from the center of the curve is s by theta is equal to 2 pi r by 360, right? So 36 by theta, which is equal to 2 pi r is known by 360, you will get theta is equal to 10.58 degree, or you can convert to 10 degree, approximately 32 minutes something, right? So you have obtained this angle also. Now in the right angle triangle, you know the theta, one hypotenuse you know. From that you are able to determine this, right? Cos theta is equal to 198.17 minus x by 198, that is r minus x by r, right? We require the x. If you substitute all the values, you will get the value 3.37. that is the required thing. Single offset. If for the entire curve, similarly we are having the formula that directly you can substitute that formula, that data, and you will get the each x value from the distance x value, right? So I hope you understood that. We continue the angular method of setting out the curve. Majorly compared to the linear method, in linear method, when the radius of the curve is large, understand friends, when the radius of the curve is large and the long chord are very small, right? And the tangent distance are very small. They were mostly the linear method is adapted. When the curve length is high, say the railway curve or a huge major national highway road, there will be huge curves, right? So when such type of huge length of curve has to be set out, predominantly we adopt angular method used when length of the curve is large, more accurate than the linear method. Since we are angle based, we are going to use the theodolite. Compared to the any other instrument, the accuracy level get increased, right? So in the angular method, there are three methods is available. Rankine method of tangential angle, or one theodolite method, and the advanced version of Rankine's method is the two theodolite method. If in the two ends of the T1 and T2, two theodolites were used based on the same Rankine methods, it is two theodolite method. And the tachometric method, instead of using the tape or chain, we can use the constants for setting out the curve long chord length by constants values, right? So that is tachometric method, right? We will see the Rankine's method. This method is useful for setting out a circular curve of long length, again the long length of the curve, and of large radius. Radius also very large, and the curve also too large. See, from T1 to C, this is the midpoint, still it continues, right? So that is the point when it yields good result, except when the chords are long as compared to the radius. When this chord length is too higher than the radius, some inaccuracy may happen, right? So that the variation between the length of the arc and its chord become considerable. It is quite accurate and is frequently used on highways and railways. A deflection angle to any point, this is to be remembered, friends. From here to here, this concept you have to remember. The deflection angle to any point on the curve is the angle at point of commencement, say T1, between the tangent and the chord from the point of commencement to that point. From the property of a circle, this deflection angle is equal to the half the angle subtended by the curve. See, from the tangent to the chord to be set out. Say if this is a small chord, from this tangent, this angle is called, they have mentioned, between the deflection angle. So we have already seen about some delta deflection angle at the point of intersection. Is there any relation? We will see. See, this deflection angle is equal to the half the angle subtended by the arc of the center. Say there is an angle will be formed at the center of the radius to the T1 to T2. There one angle will be formed. It is equal to the twice that of this total angle from tangent to the full long chord, right? Let us freeze the notation. T1 is the point of commencement, and A, B, C, etc. are the points on the curve. Say A, B, C. It's keep on going. Small del 1, del 2, del 3, etc. are the respective deflection angles. Small deflection angles between the chords and the respective tangent at T1, A, B, etc. This del 1, del 2, del 3, etc. are the total deflection angle to the point A, B, and C. See, for the point A, this del 1 is equal to del 2, it from the tangent to this chord, right? For the point B, this is the chord, and this will be the total angle, that is del 2, but from this chord to this is another del 2, small del. So the summation of del 1 plus del 2 gives this del 2. Similarly, del 3 is equal to this del 1, del 2, del 3 summation gives the del 3. It's keep on going until it reaches from T1 to T2. From when it reaches T2, what will be the total angle? That will be the capital delta by 2, right? So from the property of a circle, that the angle subtended by a chord at the center is twice the angle between the tangent and the chord. This is the property of the circle, you have to remember from the. Then, so angle T1 OA, what is T1 OA? T1 OA, this angle is equal to 2 times angle IT1A. What is IT1A? IT1A. This angle is 2 times compared to this angle, right? So here it forms the delta 1. So here it is 2 del 1. That is the property of circle, right? Property of the circle and the tangent, right? So which is equal to 2 del 1, right? Now R into 2 del 1 is equal to the chord length. What is chord? Say T1A is the chord, right? This chord subtended an angle 2 del 1 and these are tangent. This is the chord, this is the radius of the curve. So R into 2 del 1 is equal to the chord length T1A. Let's say C1 is the first chord. So del 1 is equal to C1 by 2R. It will be in radians. So to convert to degrees, product by 180 by pi, you will get in degrees. Even it will be in minute only, so we will try to convert to minutes also. And in short, you will get del 1 is equal to 1718.9 C1 by R minutes. Similarly for del 2 is C2, and for del 3 C3, it's keep on going. Then what is C to C? From T1 to B is C2, T1 to C is C3. Let's keep on going, right? So this is the formula to be remembered. In general, del n is equal to 1718.9 Cn by R, right? In general, you can remember like that. So already I have explained about for the first chord T1A, the deflection angle is del 1 is its tangential angle del 1. For second point B on the curve, the deflection angle is del 2 is angle IT1B. Let the tangential angle of the chord AB is equal to del 2. That is the angle between the tangent at A and the chord AB. The angle subtended by the chord AB at T1 is angle AT1B is equal to del 1. So that this capital del 2 is equal to angle IT1B is equal to IT1A plus AT1B. It's a summation of del 1 plus del 2, which is equal to the capital del 1 plus small del 2. Similarly, if you continue for del 3, it is del 1 plus del 2 plus del 3. So del 1 plus del 2 is again del 2 plus del 3. It's keep on going up to del n. It goes to del n minus 1 plus del n. So this del n can be checked by the last del deflection angle must be equal to the angle subtended by the curve to the radius center, circle center delta by 2. It must be equal to. If that is achieved, our calculation is also right, and we can set that same in the ground also. I hope you remember this formula, friends, right? So we will see the problems in the next videos.